All right, everybody. Today we are going to be reviewing Unit 5, which was dealing with probability. Um, and this video is going to go over the cheat sheet I made for this unit, just like I made for Unit 1 and Unit 3. Um, since probability, these problems, there's not like a lot of vocab or like formulas or anything. I put an example for each type of problem just so it's easier to understand because it's just makes a lot more sense when you're working through examples for these problems. All right. So first thing, this is a general rule with the vocab. When we're using the word and, that means that usually we're going to multiply the events together. And then if we're dealing with a problem and they're using the word or to combine two different events, that means that we're going to add those probabilities together. So you can think about and, we're going to multiply, and then or, we're going to add. Okay, so make sure that you kind of differentiate those. It's kind of like a little kind of way to remember when to add and when to multiply these probabilities together. Now, there's three different types of probability questions that are going to come up on the AP test. And these are all just straight probabilities, not random variables. We're going to review random variables unit 6 in a couple of weeks. But the first type of probability question is dealing with a two-way table. So a two-way table, remember, looks like this. This is where we have results from a study where we have two categorical variables, just like this. I'm going to go back and explain that in a second. And the second type is when we have Venn diagrams. If we have a Venn diagram, we use that to solve a problem where there's overlap between two or more categories. And then last type is a probability tree, which we're dealing with conditional probability, which means one event has an effect on the other. And it's like a chronological events of something. It's like the probability of that somebody passes stats. What's the probability that they're going to pass English? Okay, so where one event affects the probability of another, then we're going to build this tree diagram out to solve those problems. So let's go back and start with the two-way table. So we can see here we have a two-way table for this medical study. That's 780 people determining their age, whether they're below or above the age of 55, and then whether they have had this heart stroke. So again, a two-way table, we have those two different categorical variables, and this table is summarizing all of this. And a lot of times we're going to want to do probability calculations because it's hard to really just look at this raw data and come to conclusions from it. So we're going to go through and do three different parts of this question. So part A said, which is the probability that the person had a heart stroke, or what is the probability that the person had a heart stroke? So when we're dealing with these problems, we want to first see if there's a restriction that we're dealing with. Okay, so it said given somebody was younger or equal to 50, that would be a restriction, and we're only going to look at that column. Let me circle that for you. So if I said younger or equal to 50, then we just look at this total right here. Or if I said, given that the person has had a stroke, what's the probability that they are older than 55? I would put that right there. So now part A, it says, what's the probability that the person had a heart stroke? There's no restrictions there. So if there's no restrictions, we're just going to use the total of everybody. So the 780. So that goes under our denominator right there. Now to figure out the numerator, it says, what's the probability that they had a heart stroke? So again, there's no other restrictions within that heart stroke, so we're going to look at everybody total that had the heart stroke, which is the 104, and we put that on top for the numerator, when we calculate that out, it comes out to 0.2167. All right, so that numerator is going to be what the question's asking for, and then the denominator, the bottom of the fraction, is going to be your total. Let's move on to part B. So part B says, which is the probability of being older than 55 and at the same time having had a heart stroke? So again, there's no restriction at the top of this, and say given that the person was older than 55 or given that person has had a heart stroke. So we're still going to use the 780 as our total right here because there's no restriction to who we're looking at. We're looking at everybody in the study. Now it says, what's the probability of being older than 55 and at the same time having had a heart stroke? So we're looking at older than 55, and we're only looking at people that had a heart stroke, so that's going to be 75. That's what we put in our numerator. We divide those numbers, and it comes out to 0.0962. So that would be your probability for part B. Okay, so now moving on to part C, it says if the person selected is older than 55. So that first part, that's a restriction. So that means that we're only going to look at people that are older than 55. So our total is going to go from this column right here, and we're going to use that 350 and put that as our denominator. Then for our numerator, was probably that they had a heart stroke. So since we're only looking at people older than 55, we're only looking at this column, we're going to use the 75 and put that on top. And that gives us the probability of 0.2143. So again, make sure you're looking through those restrictions. Okay? Another type of problem that you could see on this is having two events that are connected by the word or. So what's the probability that somebody would be younger or equal to 55 or that they had a heart stroke? So for those, you want to add those probabilities together, and if there's an overlap, you want to subtract it, which we're going to talk about in this next section. So now, the second type, probability, the Venn diagram. Like I said, this is for probability problems where there's an overlap. Usually it's just going to be two different variables, but it could be more than two, but most likely it's going to be two different variables that you're dealing with. So for this one, it says, this author found that 14% of married men buy both flowers and jewelry for their wives for their birthdays, 58% of married men will buy jewelry, and 39% will buy flowers. So the reason that we're going to set up a Venn diagram for this question is because there's an overlap, right? Because we have 58% that bought jewelry and 39% that bought flowers. And you can see, and then we have 14% that bought both. So if there's an overlap, we have to account for that overlap. And a way to kind of help give you a check, if I added up all these probabilities, they're going to be over 100%, which isn't going to make sense, right? So that means that there is an overlap that we have to account for. So we're going to set up this Venn diagram. The first thing that you want to put down is just going through it. It's kind of just in order of the problem. So we know that 14% of married men bought both of these. So we're going to set up the flowers right here and another circle for the jewelry, and then the center and the part in the center is the overlap right here. So the overlap is people that bought flowers and jewelry. So we put that in the middle, which is 14%. So we put that right there in the middle. Then we know that 58% of married men will buy jewelry. So I put 58% on the outside next to our column right here. So that tells me that 58% of men bought jewelry, and then 39% of women or men bought flowers. But again, like I said, there's an overlap. So the way that you count for the overlap, and the overlap is going to be on the outside edge of these circles right here. So the way that you get that 44% is to do 58. So the total number of people that bought jewelry minus the people that bought both, which gives us 44%. So that's 44% of men only bought jewelry. And then there's that 14% that bought jewelry, but then they also bought flowers. And then we do the same thing for the flowers. So 39% of men bought flowers, but then there was an overlap of 14, so we subtract that, which gives us 25, which means that 25% of men only bought flowers, and again, 14% bought both. So if we look just at the numbers in our Venn diagram right here, 25% of men only bought flowers, 14% of men bought flowers and jewelry, and 44% men bought jewelry only. Now, the last part of that is dealing with neither. Okay? So once we get all these numbers, we add them all up, and that gives us the total percentage of people that fell in one of those three categories. So percent of men that bought flowers, bought jewelry, and then percent that bought both. So when we add up all of those together, 25 plus 14 plus 44, that gives us 83. So 83% bought one of those two, at least one of those two different items. So then to get the percentage that bought neither of those, none of those, then we subtract it from 100, which just gives us the 17%. So I'm going to put that the outside part of the Venn diagram. So 17% of men bought none of those for their wives on their birthday. So now, once we get this Venn diagram, answering the questions like common sense. Okay, so as long as you can set up this Venn diagram, answering the questions is so easy. So let's read through what the question's asking. What's the probability that a randomly selected man will buy flowers but not jewelry? So let me erase all this. It's a little bit easier to see. Try to get some of this clutter off here. There we go. So, what's the probability that they will buy flowers but not jewelry? So we look at the flowers, and then the probability that they do not buy jewelry. So we got to exclude the both, right? Because if they're not buying jewelry, we can't have the overlap there. So your answer is going to be the 25%, because that's the percent of men who only bought flowers. And that's why 25% is your answer for that problem. All right, then last part of this video is dealing with the third type of probability problems, which is our probability tree. So again, this is where we use these problems to, anytime there's a probability problem where there's events that are affecting another. So maybe an example would be, given that somebody is pulled over for speeding, what's the probability that they are intoxicated? Okay, that's a probability of conditional probability, because you have that first probability that they're speeding, and then the second probability that they're intoxicated. All right, so we have this example dealing with athletes from high school to professionals that we're going to look at. So the first, anytime we're doing this, anytime we're doing an event, you want to label the event right here, and then have the different options at the end of the branches of the trees. So only 5% of male high school basketball, baseball, and football players go on to play at the college level. So that's going to be my first event. So I make my tree diagram right here, my branches, and there's just two different options. Yes, they play at college. No, they don't. So 5% Can put it as a decimal, 0.05. Played at college, 0.95. Didn't play at college. That's my first event. Let's go on to our second event then. So it says about of these, so that means of those high school athletes that play on college, only 1.7% enter major league professional sports. So they play in the pros. So that's going to be our second event. They make the pros. Again, just two options, yes or no. 0.017. We do the inverse of that to 0.983. And that's how I got the 0.95. Since there's just two events, you just subtract them from 1. Okay, because they have to add up to 1, or if there was a percentage, now the decimal will have to add up to 100%. Then the last event is about 40% of the athletes who compete in college and then reach the pros have a career of more than 3 years. So then that third event is of the people that make the pros, 40% have a career that lasts longer than 3 years. So we're going to just yes or no, and then we do the 40% that do, and then the 60% that don't. Again, we're doing the inverse of that, so you subtract that number from 1. Once we get this diagram, it's going to make this problem a lot easier to do. These questions are very tricky, a lot of really particular wording, and if you draw this diagram, it's going to make it a lot easier. Even for me, I've been doing these problems for a long time. It'd be hard for me to solve this problem without doing the tree diagram. So make sure you're taking the time, even if it's a multiple choice question on the test, that you're taking the time to draw out this diagram. So the question is asking, what is the probability that a high school athlete who plays basketball, baseball, or football competes in college, then goes on to have a pro career of more than 3 years? So anytime we're doing this, we want to think about, just follow the tree down to the different events that it's asking. So what's the probability that a high school athlete competes in college? So we're going to go, we'll do this a different color. Do green so you can see this. So we're going to go down this branch because they played in college, right? So we're going to go down, they play in college. Then they reach the pros. So we go down this branch. And they go on to have a pro career more than 3 years. So we go down this further branch. And anytime you're at the end of a branch like this, to find that probability, you're just going to multiply them together. So you do 0.05 times 0.017 times 0.40, and that gives us 0.00034. On your calculator, that's going to give you scientific notation, which is 3.4 e to negative 4 power, which means that we bring that decimal place over 4 spots. So you're going to have 3 zeros in front of that. So that's how we do conditional probability problems. And again, you draw that out, tree diagram out, and then just go down the branches for what it's asking you in the problem. So hopefully this video kind of help review everything. We're going to have a couple more practice problems to do for this unit. So hopefully you can use this and then get those questions right and feel comfortable when these questions come up on the AP test next month.